Hello and welcome to the first part of Lesson 2. This lesson is intended to be a survival guide for the various bits of mathematics that we'll be using throughout the course. It's by no means a complete and rigorous maths course, but hopefully it will be a useful reference for you. We're going to start in this part of this lesson by examining scalars, vectors and tensors and their associated operations. In the following parts of this lesson, we'll examine aspects of vector calculus, we'll solve some first-order differential equations, and we'll introduce ourselves to complex numbers. One of the key learning objectives for this part of Lesson 2 is to give some examples of how to create tensor quantities and how to calculate the magnitude of vector and tensor quantities. Another important outcome is that we'll define exactly what we mean by certain operations, as the literature can be somewhat confusing at times. Throughout, I'm going to give some worked example of these vector and tensor operations and also introduce a compact notation, summation notation, that can be used to precisely define the operation that's being undertaken. So, let's start by reminding ourselves about scalars, vectors and tensors. So a brief synopsis is that we're going to look at some scalar quantities in rheology. These will be properties that you're familiar with. We're going to look at some vector quantities in rheology and some associated vector operations, such as inner products and outer products. We're also then going to look at tensor quantities in rheology and some selected tensor operations. So let's start at the beginning and let's think about scalars. If we were to look for a dictionary definition of scalar quantities, it would be roughly along the lines of scalar quantities are fully described by a single number, and that number represents a magnitude or a size. So, if we think about some familiar rheological properties, let me put on the board a picture of some water flowing out of a tap and some picture of some honey flowing off a spoon, and we would see that the way these materials are flowing are very different. They have different viscosities. The water has a relatively low viscosity, about a millipascal second, and the honey, especially if it's cold, has quite a high viscosity, of order 10 pascal second, 4 orders of magnitude higher. However, if we think about viscosity, that number is all we need to know. The viscosity of the material is fully described by that single number. And if we think of another material property, density, we can say exactly the same thing. So shear viscosity, denoted with the Greek symbol mu, and density, denoted with the Greek symbol rho, are both scalar quantities. On this course, we're going to be defining scalar quantities by italic and non-bold typescript, as I've shown there on the blackboard. And so whenever you see that, we'll know automatically that the property in question is scalar, which differentiates it from how we're going to denote tensor and vector quantities. Now, believe it or not, we can actually think of scalar quantities in a tensorial manner. And hopefully this will become quite clear, but I'm going to say that scalars are zero-rank tensors. The rank of a tensor is a description of how many dimensions that tensor has. So a vector has one dimension, it's a first-rank tensor. The stress tensor we'll be looking at is basically an n-by-n matrix. It has two directions. Scalars are zero-rank tensors. All they have is just a size. So if we get used to thinking of scalars as zero-rank tensors, it helps to put the rest of the material we're looking at into some kind of context. So let's think about vector quantities. Again, if we were to look at a dictionary definition, it would be along the lines of vector quantities are fully described by both direction and magnitude. And we can think of this with respect to velocities. So let's have a look at this nice mountain scene. It looks like Wales on a nice sunny day. And I've highlighted in the circle there a waterfall. So if we think of a water droplet in this waterfall, we know that that water droplet's going to have a velocity, probably upwards because the wind is so strong, but we know that that velocity can be broken down into each of the coordinate directions, the x, y and the z direction, or arbitrarily it can be the I direction, the j direction and the k direction. Because we're not always dealing with Cartesian coordinate systems, we may be in cylindrical polar or spherical polar, but we can generalize the different mutually orthogonal coordinate directions by the I, the j and the k. So if we think about velocity, the velocity is a vector. that water droplet is going in a particular direction, but we can break it down into components of that velocity in each of the 3 coordinate system dimensions. So v1 in the I direction, v2 in the j direction, and v3 in the k direction. We can compactly write this as a column vector, where v1 is stacked above v2 and v2 is stacked above v3, and each entry in that column denotes which part of the coordinate system we're using. So, throughout this course from a typographical standpoint, vector quantities are going to be denoted by non-italic and bold symbols. And as I've already alluded to, if we think about rank of tensors, that vector quantity that I put on the blackboard has now 1 dimension. It's got a column. And so we call vectors first rank tensors, and we can think of this as a 3x1 matrix. So let's think about how we can operate with vectors. First and importantly, we can only add vectors to vectors. We can't add scalars to vectors. We can't add tensors to vectors. So we can only add like to like. So for example, we might add v to itself to give us 2v. So v plus v gives us 2 times v. But note, 2 there is a scalar. So we can multiply these vectors by a scalar, but we just can't add scalars to a vector. And the result will just twice v1, v2, v3. So let's think about multiplying vectors. Now, there's a number of ways and a number of products that vectors can be subjected to. We're only going to think about 2 of these. We're going to think about a product operation that decreases the rank of the product. So it goes from 1 to scalar, 1 to 0. And this is the inner product. You might know this as a dot product as well. So let's briefly look at that. Let's say that we have the dot product of a velocity vector v with another velocity vector u. Now, we can write this as v transpose u, because when we take this inner product, we want a row vector operating on a column vector, hence that transpose. And so in vectorial form, we might write it as so. You can see on the board there, my first vector is now a row. That's the transpose. We're swapping a column to a row. And it's dotting with the column vector that is that second velocity vector u. So when we take this inner product, or this dot product, we result with a scalar. And what we do is we multiply the first element in the row with the first element in the column. Then we add that to the product of the second element in the row to the second element in the column. And we add that to the product of the third element in the row to the third element in the column. And so v1u1 plus v2u2 plus v3u3 gives us the inner product, and that is a scalar quantity. So we've decreased the rank of our vector by 1 from a rank 1 to a rank 0. Now, there was a very clever chap at the turn of the 19th century, Albert Einstein, and amongst all the amazing things he did, he also invented a notation for compactly describing how we operate with scalars, vectors, and tensors. So Einstein's summation convention, which I'm going to call just more simply as summation notation, can describe very precisely how we do this inner product. For example, v dot u, what we want to do, is written in summation notation as v subscript I, u subscript I. What that means is that we are summing over a counter I over the number of dimensions that we've got in our coordinate system, in this case 3. And what we are summing is a product of v subscript I, u subscript I. So when I equals 1, it's v1u1. When I equals 2, we're adding that to v2u2. When I equals 3, it's v3u3. And so for computer programmers, you can think of this as like a for loop. And we're just looping through I and adding together the product of what ith element is given by vi and ui. So summation notation is incredibly useful, especially when we get to higher rank tensors, because it's not always easy to visualize what it is that we're doing. So let's look at this second way that we can multiply vectors together. We've decreased rank by 1 with the inner product. What we're now going to look at is increasing the rank by 1. to a second rank tensor by something called the outer product. And this is an operation that we will be doing quite a bit in lessons to come. So, the outer product of v with u is written as I've shown on the board. That cross that's inside a circle is the symbol for an outer product. However, rather unfortunately, this symbol is barely ever used in the literature, and you have to kind of infer that an outer product has happened just by looking at the properties of the result of it. So, in the literature, you'll often find v outer product u just simply written vu. What that means is that we're actually operating with a row and a column again, but this time the column vector comes first and the row vector comes second. So we'd write this out in longhand as follows. So v is our column vector, u transpose, swapping columns to rows, is now our row vector, and we end up with a matrix of products. And if we look at the operation that we're doing, the top row of the answer is the top row of the column vector multiplied by the only row of the row vector. And so the position in each of the columns in the final result is dependent on each of the columns in that row vector. So we've got v1u1 in the 1, 1 position, v1u2 in the 1, 2 position, v1u3 in the 1, 3 position. And then we drop down an element in the column vector and do the same thing. And so we've got v2u1, v2u2, v2u3 in the 1, 1, in the 2, 1, 2, 2, and 2, 3 position in the final matrix. And then again the same for the final row there. So we've increased the rank by 1, we've made a second rank tensor. This is good. Again, we can look at this operation in summation notation. So vu, note I've written it without the outer symbol product there, which is unfortunately what you're going to have to get used to seeing. I say this time we've got viuj, where j is a separate counter, and then we've got these two e hats. These e hats are components of a basis vector, and e hat I and e hat j tell us where in the final matrix the answer goes. So let's expand this and I'll talk you through it. So this time, because we've got an I and a j, we've got two summations happening. For programmers, think of this as two for loops, one nested inside the other. We always count the letter in the alphabet that's later first. So we count j first. So we set I equals to 1, we count through j from 1 to 3. We set I equals 2, we count through j equals 1 to 3. We set I equals to 3, we count through j equals 1 to 3. And each time we do that counting, we're multiplying together vi, so when I equals 1 it's v1, uj, if j equals 2, u would be u2. Then ei, ej denote the row and column that the final product goes in. So if I equals 1 and j equals 1, we have v1 u1, e1 e1, and so the final result goes in the 1, 1 position of the matrix. Likewise, if I equals 1 and j equals 3, we'll have v1 u3, e1 e3. So that is the 1, 3 position, the top right-hand corner of the resulting matrix. So we can decrease rank by 1 with inner products, we can increase rank by 1 with outer products. Now, before we move on to second rank tensors, I'd just like to remind you of how we can apply these two types of products. So v.u, the inner product of v with u, is the same as the inner product of u with v, so that's fine. If we look at a bracket of, let's say, two vectors added together, u plus w, and then the dot product of that entire bracket being taken, we have this distributive property where v dot u plus w is just the same as v dot u plus v dot w. And we have essentially the same thing going with the outer product. So with the outer product, v outer product u is the same as writing u outer product v, but then transposing the whole lot, turning rows into columns and columns into rows. Also, if we think of the outer product in a distributive manner, v outer product u plus w is just simply v outer product u plus v outer product w. Okay, so now's the time to move on to second rank tensors, our n by n matrices. And let's look at some of the quantities that can be described by these tensors to start with. So again, if we look at a dictionary definition, it would be along the lines that second-rank tensors have direction and magnitude, but the magnitudes also act on specified planes. So let me just talk through this in a little bit of detail. On the board, I've put a picture of some wonderful folded sedimentary rock. What I want to do is to zoom in on that rock and think of the enormous stresses that have acted on this rock through geological history in order to actually fold it in the first place, because stress is a second-rank tensor quantity. So let's zoom in on an arbitrary layer of rock, and let's place our coordinate system in I, J, and K. So mutually orthogonal, but we haven't specified whether it's Cartesian or cylindrical or whatever. You can think of this for the purposes of this example to be Cartesian though. And now let's mark on some stresses. So let's say, acting on the K plane, now we define a plane by the direction of its normal, and so in this case a horizontal plane will have a vertical normal, and vertical here is described by the K direction, so the K plane is the horizontal plane. And I could have a stress acting inwards onto that plane. So the stress is acting in the K direction, or the negative K direction, but also on the K plane. However, I could also have a stress that also acts on the K plane, but in shear. It's sliding along the top of it. And so in this particular example, that stress is acting in the ith direction. But they both act on the K plane. And so we could also, if I'd drawn this diagram in 3 dimensions, have a J direction force acting on the Kth plane, and again it would be sliding into or out of the screen in shear. So we can have on every plane stresses acting in each direction of our coordinate system. And of course we've got as many planes as we also have directions in our coordinate system. So we could look at a different plane. Let's look at the ith plane. And again, the I plane is vertical because that is the orientation with which you'd get a normal vector pointing in the I direction. And so if we think about a stress acting on this ith plane inwards in the I direction, so it'd be negative in the I direction, again it would be a principal stress acting on that vertical face. We could also have a shear stress acting on that vertical face as well, but now let's say the direction in which it's acting is in the Kth direction, but it's still acting on the I plane. So we can see that in order to fully capture stress, we need a structure that can handle, in this case, 9 different numbers. So it's a 3x3 matrix. So second-rank tensors on this course are going to be denoted by non-italic and bold symbols, which is exactly the same notation as for tensors, as for vectors, apologies. So this can be a little confusing at times, but you'll soon learn to recognize which quantities are vector and which quantities are second-rank tensor. So all the second-rank tensors we'll see on this course are n by n matrices, but there's nothing stop us from having a tensor that's n by m, but we won't be worrying about that. So let's now think about operations that we can do with second-rank tensors. And it's probably going to come as no surprise that there's actually quite a lot of products that we can form with second-rank tensors. However, we're only going to concern ourselves with 2 of these products. Both of these products end up reducing the rank of the answer. So let's think about the first one. If we want to decrease the rank by 1, as in we get a vector answer, we're going to take an inner product. Now we need to be a little bit careful here, because the inner product is actually between a vector and a tensor. Let's say we've got a velocity vector v and a stress tensor tau, then we would write in longhand our velocity vector as our row vector, and our second-rank stress tensor with each of the elements expanded out. So if we're to take an inner product of these 2, we would end up with a column vector. Now we can think of this as effectively just 3 consecutive vector inner products, because we can imagine this tensor quantity to be 3 column vectors stacked side by side. And so if we look at each row in the answer, the first one comes around through operating the row vector, the velocity vector, with the first column vector, as I'm calling it, which is the first row of our second rank tensor. So v1 tau 11 plus v2 tau 21 plus v3 tau 31 is the first row of the answer. And likewise, the second row of the answer will now be operating on the second column vector that's stacked up, the second row, second column of our tensor. And the third row of our answer will be involving the third column of our second rank tensor. So in summation notation, we can think of this as follows. If we look at how it's written, we've got v subscript I, tau subscript ij. So again, we're using two summing loops. First one involving I, second one involving j, and we know we use j first to count up, and then increment I, and then count up with j again, then increment I, then count up with j again. So if we start that off, we have I equals 1 and j equals 1, so we have v1, tau 11, and ej, remember this is our basis vector and it tells us where in the final answer the answer goes. And so v1 tau 11 will appear in the first row, e1, of the resulting vector. And we can see v1 tau 11 there in pink. So if we increment j from 1 to 2, we have v1 still, tau 1, 2, and that appears in the second row of the answer. Increment j again, v1 tau 1, 3 appears in the third row. Okay, and then we set j back to 1 and increment I to 2, so I'll have v2 tau 2, 1 appears in the first row, and so on and so forth. So again, Einstein notation there, or summation notation, being very, very useful to denote what actually goes on with these operations. So if we can decrease the rank by 1, we must be able to decrease the rank further because we're effectively starting with a two-dimensional quantity. We can decrease the rank by 2 to a scalar with something called the double dot product. So let me illustrate that for you. If we imagine we have stress double dot producted with stress, we would write in longhand the two matrices out thus. Now, when we're doing the double dot product, we can effectively think of this as the vector product, so the vector inner product, of 3 row vectors, which is our first second rank tensor, with 3 column vectors, which is our second rank tensor, where each of the answers to that inner product also gets added to the next one. Let me just demonstrate. So the answer written in longhand would involve these 9 terms here, and we can see that they're constructed by saying tau 11 times tau 11 plus tau 12 times tau 21, tau 13 times tau 31. Then we drop down a row in the second, in the first matrix and go across a column in the second matrix and do the same thing again. And then we drop down a row in the first matrix and across a column in the second matrix and do the same thing again, like so. And so we can see that we end up with a big summation of all these 9 terms, and that final summation is indeed scalar. Now, using summation convention, again we can do this, and note we now have no basis vector there because we've got a scalar result. And we've got 2 loops still because we're dealing with second rank quantities. And so in the summation we have tau ij, tau ji. So we can see that we're always adding, let's say, 1, 2 to 2, 1, or 3, 2 to 2, 3, as we increment through j, and then increment through I. So, second rank tensors can be operated on by a vector to give a vector result, or we can operate on 2 second rank tensors together to give a scalar result. And if we were ever to want to find the size or the magnitude of a second rank tensor, it's this double dot product that we use. We're soon going to encounter a second rank tensor called a strain rate tensor. It gives us a lot of information about rates of deformation in a velocity field. Sometimes, however, all we want to know is the magnitude of the strain rate. And we'll see when we talk about generalized Newtonian fluids in lessons to come, that will give us a quantity with which we can apply rules about shear thinning. So, if we want to find the magnitude of a tensor, we do the double dot product of the tensor with itself, We divide that by 2 and take a square root, and that gives us the magnitude. So let's sum up a few key points. This whole part of this lesson was around scalars, vectors and second-rank tensors, and we will be seeing quantities that have these properties all throughout rheology. We mentioned viscosity for scalars and density for scalars, velocities for vectors, and stresses for second-rank tensors. The key thing you've got to remember is you can only ever add like to like. You can only add scalars to scalars. You can only add vectors to vectors. You can only add second-rank tensors to second-rank tensors. However, we can multiply scalars, vectors and second-rank tensors all by scalars. And the answer is just a scaled result of what we started with. However, if we want to multiply vectors and second-rank tensors by anything else other than a scalar, we have to be very keenly aware of what exactly we're doing in terms of that product. We've seen that various products can increase rank, other products can decrease rank, and we've only examined here a subset of the sorts of products that we can carry out. So, if you want to find out some more information about this, please have a look through pages 12 to 53 of Faith Morrison's book. There's a lot more depth explored there than we've gone into here, because I've only covered the essential bare bones here that we're going to need for these lessons. But if you're keen and want to find out more, then you'll find a lot more there.